tested on any of this, but it's just too cool not to mention. It is incredibly complicated. For a rough idea, it took Einstein 10 years of work after special relativity to figure out general relativity. We're not going to do much with it, of course, except there's a surprising amount we can understand and appreciate. First, if we make measurements only at one point, so we'll call them local measurements, we couldn't tell the difference between being in a box on the Earth and being in an elevator that's being accelerated through space at 9.8 meters per second squared. Our experiments all give the same results. If we did an early physics 1 experiment of dropping a ball and timing it with a stopwatch, you wouldn't be able to tell if you were parked on the Earth or being pulled by a rocket through space at 9.8 meters per second squared. Now, if we measured it more than one place and we were very, very precise, we would see some differences. For example, in the elevator being pulled through space, the balls will fall on parallel tracks to the floor. The elevators parked on the Earth, though, the balls will actually approach each other just a little bit because they're both trying to fall towards the center of the Earth. Now, think about what happens if there's a tiny hole in the elevator and someone shines a light through it. It doesn't take light very long at all to cross the elevator, but it does take some finite amount of time. And while the light is crossing the elevator's moving up. So rather than hitting straight across, it drops just a little bit and hits a point slightly lower than that. So if it's going to work the same on the Earth, that means light falls in a gravitational field. Not much, but it will fall just like any other projectile. Now, this has been measured very, very precisely, but if you remember refraction, we saw that light bends if it changes speed and it curves towards the low speed thing. The same thing happens here, and the reason is time itself moves a little bit slower closer to the Earth than far away from the Earth. It's a ridiculously small effect for the Earth. The odd thing is it doesn't depend on the gravitational field, but the gravitational potential. We talked about this when we first looked at voltage because this is a gravitational version of voltage. And if you remember, I told you I could only think of two places where gravitational potential was important. One of them was the height of water, and the other one is this. Remember, there is a difference between potential energy and potential. If we're close enough to Earth to just use little g for the gravitational field, the potential difference between 2 points is gh. The time dilation factor associated with that, 1 minus gh over c squared. That c squared is what makes this usually insignificant. That means if we had a 1 kilometer building, which is taller than anything currently built, a clock up there would run faster, at the top of the building, would run faster than a clock in the lobby by about 1 part in 10 trillion. So if you spent 32 years at the top floor of the building, your clock would be faster than the one on the ground floor by a tenth of a millisecond. Now, even though this is a ridiculously tiny factor, it's been measured over and over again with atomic clocks. And one of the earliest tests involved putting atomic clocks on two different planes going around the Earth in opposite directions. And when they brought them back together, of course, they didn't match anymore. And the deviation that they measured matched the prediction. Now, places where it's not a small factor, if you were to get near a black hole or a neutron star, even the name black hole is actually something from Western physics. The Russians called them frozen stars because as the star collapses, once the mass gets concentrated to a certain point, somebody far away watching is going to say that the time has gotten so slow that it stopped. Now, if you fall into a black hole, you'd be able to see how the whole universe ends because it would take an infinite amount of time, as far as the rest of the universe is concerned, for you to fall in. For you, it would happen very quickly, and you wouldn't be able to tell anybody what you saw anyway. Now, at this point, you may be thinking this is just too much in the way of changes to Newtonian physics. It's crazy to find out that all this stuff is happening. Remember that Newtonian physics works good enough for just about everything, including putting satellites in orbit. It's hard to do measurements that even detect a difference between Newton and Einstein physics. Is this something that could ever affect your life? It turns out there is, if you use the Global Positioning System, the GPS. Basic idea is there are a few dozen satellites. Now, several countries have their own version of this. Um, Usually, there's a few of them in your part of the sky at any given moment. They are atomic clocks that are essentially sending out the time constantly. Your phone picks it up and calculates the difference between when the signal was sent and when the signal reached you to get your position on the globe. This is kind of like the counting the seconds after the flash of light until you hear thunder in a storm. This is using the travel time of light, though, not sound, and the timing is critical. And the reason is if you want to know your position to within 10 feet, you have to be able to measure times to better than 10 nanosecond accuracy. What if Einstein had just discovered special relativity, but no one had discovered general relativity by the time the GPS system was put in place? The satellites would have had to have their clocks corrected for their gamma factor, since we would say they move slower. So what we would do instead of sending up a regular laboratory atomic clock is we would send one up that's a little too fast if you kept it on the Earth. The size of the change is small, it's only 7 microseconds per day, but if you ignored it and sent up a regular atomic clock and you start building up an error of 7 microseconds per day, that's 7,000 feet per day. What if they knew about special relativity, they sent up the clocks that are a little bit fast, but they didn't know about general relativity? Clocks at GPS satellite altitudes are actually too fast by 46 microseconds per day. So if you only corrected for special relativity, you would be losing about 9 miles per day in accuracy, and pretty quickly you could just guess your position to be better than GPS. Because these two effects fight each other, but they're not the same size, the clock in the GPS satellite is made so that if you parked it on the Earth, it would be 39 microseconds slow every day. In the correct orbit, the relativistic effects cancel out and we get working GPS. So if you've ever used your phone to find out where you are, you've done tests of both special and general relativity.